In this video, we're going to finally look at the complete picture of a linear programming problem. So far we've learned that a linear programming problem has some sort of objective function that we either want to maximize or minimize. And these linear programming problems require that our objective function is linear in form. So we haven't mentioned this in a previous video yet, but we're assuming that our objective function, maybe this represents our revenue that we want to maximize or some sort of cost that we want to minimize, and the objective function itself does need to be linear. So you see that we have a constant times x to the first plus a constant times y to the first, where x and y are our two unknowns. We call that the objective function, and it's subject to a number of linear constraints of the form cx plus dy is less than or equal to e. So point here is we have a linear expression less than or equal to a constant or potentially greater than or equal to a constant. The solution set of points xy satisfying all constraints is called the feasible region. So we'll see this below. When we graph all these constraints and we see where the region that they share in common, we've developed the feasible region. And the largest or smallest value of the objective function is called the optimal value, and a pair of x and y that give the optimal value constitutes an optimal solution. So we've kind of alluded to this intuitively, that our optimal solution, that if we have our feasible region, and here's sort of an illustration of a feasible region, these are going to be some sort of polygonal forms. Polygon, we're going to have multiple sides potentially, and then we're going to have all of these corner points, as we call them. They're corners, and so we call them corner points. And this fundamental theorem of linear programming says that if you have a bounded, non-empty feasible region, you will always have optimal solutions. So what do we mean by bounded? Well, naturally, we're already working with just the first quadrant. Those are the assumed constraints. So we assume that we're not looking for negative x or negative y values. And this is a bounded feasible region. I like to think about this as looking at it from above. If you were to put a mouse in this little fortress here, the mouse would not be able to get out because it's blocked on all sides. And so that's what we mean by bounded. We mean blocked on all sides. If an LP problem has optimal solutions, then at least one of these solutions occur at a corner point of the feasible region. Okay, at least one of these solutions occur at a corner point of the feasible region. So this is what we've been alluding to, that basically we don't need to consider points inside of this feasible region. It's not necessary. We just need to consider the corners. And one better, we don't even need to worry about the edges. We just need to test the corners themselves, which is an interesting result, and intuitively we've seen this. So let's take a look at a couple of examples. The goal here is just to work through a couple of problems to get a sense of the modeling components and how we go about solving them. First problem. The Solid Trust Savings and Loan Company has set aside $25 million for loans to home buyers. Its policy is to allocate at least $10 million annually for luxury condominiums. A government housing development grant that the company receives requires, however, that at least 1/3 of its total loans be allocated to low-income housing. Solid Trust's return on condominiums is 12% and its return on low-income housing is 10%. How much should the company allocate for each type of housing to maximize its total return? So already we see that we're trying to maximize an objective, and what are we trying to maximize? Well, the total return. Okay, well, what we want to know is how much should the company allocate for each type of housing? So we have two types of housing, namely low income, we have condominiums. So X will be the amount allocated for we'll say condos, and this is going to be in millions of dollars. Just easier, that way we don't have to spell out 25 million with 6 zeros at the end. And then Y will be the same thing, but amount allocated for, we'll just say low income housing, again in millions of dollars. So what do we want to do? We want to maximize the return. Well, how are we going to get return? We're going to get return by this percentage being applied to how much we allocate. So if we allocate X million dollars into condominiums, then our return, which I will just denote R, stands for return, but you can use any letter you want. That's the output of our function. It's going to be 12% of whatever we put into condos, plus we'll also get 10% from how much we put into low income housing. So we want to maximize R. We want to maximize the size of the return that we get, but we can't just, we can continue making this larger by making X and Y both larger, but we have limitations. Also, we can see that this is linear. It's a constant times X plus a constant times Y as the output. So this is definitely beginning to take the shape of a linear programming problem. And then our constraints, we'll say subject to, well, let's see what our constraints are. We have $25 million for loans to home buyers. Okay, well, that means that X can't be bigger than 25 million, and Y can't be bigger than 25 million. And we don't necessarily need to give away every single dollar, because not every we may not have enough home buyers to which we could allocate all of this 25 million. So we're going to say that how much we allocate for condos and how much we allocate for low income housing has to be less than or equal to $25 million. Now, since X and Y are already numbers that reflect millions, so if X was 5, that would mean 5 million. We don't need to type out or spell out 25 million. We can just say 25, and that's already in millions. So there's that first constraint. Its policy is to allocate at least 10 million for luxury condominiums. So that means how big X is. X is going to be at least, meaning at minimum, 10, but it could be more than 10 million. So we'll say X is greater than or equal to 10. Finally, a government housing development grant that the company receives requires, however, that at least 1/3 of its total loans be allocated to low income housing. Wow, okay, so how do we write that as a constraint? At least 1/3 of its total loans be allocated to low income housing. Well, its total loans, first of all, is X plus Y. And we want to make sure that what we allocate to low income housing, which is Y, is greater than or equal to 1/3 of the total loans. So I had to kind of twist the words a little bit there, but here we're saying that how much we allocate to low income housing is at least 1/3 of the sum of all the loans that we have. So we're going to write this as Y is greater than or equal to 1/3 of X plus Y quantity. Now, we can do a little bit of rearranging here. If we're going to be using technology, it's not absolutely necessary, but we're going to clean this constraint up a little bit more. We'll multiply both sides by 3. And in working with inequalities, if we think about a weighted scale, if we have, for example, that 5 is greater than or equal to 3, which is a true statement, if you were to multiply both sides by a positive constant, You can still agree that if 5 is bigger than 3, then 2 times 5 is bigger than 2 times 3. That's still a true statement. However, the only time we need to worry about our inequality sign is if we were to multiply both sides by a negative. So while we can agree that 5 is greater than or equal to 3, if we were to multiply both sides by -1, let's say, -5 and -3 are, well, -5 is actually less than -3. I could put an or equal sign under that. That's still a true statement. And the reason for multiplying by negatives is that if you think about from left to right, values grow larger, but on the other side, the mirror image of these values, -3 and -5, the larger the negative number, obviously the smaller it is. And so multiplication of an inequality by a negative value will require us to invert the inequality sign. Okay. So in this case, we're fine by just multiplying both sides by 3. That's going to give us 3y is greater than or equal to x plus y. And then I can subtract y over to give me 2y is greater than or equal to x, because we can agree that if we remove the same amount from both sides, we subtract the same amount on a scale that's already tilted in one direction, and you remove a pound from both sides, then that side that was heavier is still going to be heavier, as long as you do the same thing to both sides. And then finally, we can divide by 2 or multiply by 1/2, and we have y is greater than or equal to 1/2 x. Okay, so now that we're at that juncture, we can plot these inequalities and take a look at the value of the objective function. So we'll go ahead and do this in Desmos. X plus y is less than or equal to 25. And we can see that there's our feasible region, again, only considering the first quadrant. So far, any point in that reddish region will work. We also know that what we allocate to condominiums has to be at least 10. So x is greater than or equal to 10. And now we can see that our feasible region is this little triangular region here. So notice that it's bounded. It has walls on every side. There's no escaping this feasible region if you were to drop a mouse in there into this little pen. And then we also have y is greater than or equal to 1/2 x. Y is greater than or equal to 1/2 x. Okay, so that changes the shape of that a little bit. This big triangle was our feasible region, but now it's this triangle right here. And that is our feasible region. That's an area that corresponds to all inequalities. We can kind of see that if we add them in one by one. Okay, so now add in the second one. So now this triangle is our feasible region, and then y is greater than or equal to 1/2 x is now this triangle. So there are our 3 corner points. And what we want to do now is we're going to insert a table, and in this table, the columns are called x1 and y1. And in here we will put our objective function, which is 12% of x plus 10% of y. So 12% of x1 plus 10% of y1. And now we can put in those corner points. So that's 10, 15. And then we don't want to graph that portion, but we see that that's going to result in a return of $2.7 million. Okay, now our next corner point down here would be 16.667 and 8.333. So since this is in millions of dollars, we can, this is really 16 2/3, which is 32, 48, 50/3, I believe. 50/3, yep, that's 50/3, and 8.33 is 8 1/3, which is 25/3. So I'm just going to go ahead and enter those values as fractions, because since that's in millions of dollars, if we round, then we're actually rounding off thousands of dollars. So 50 thirds, and it'll get rounded when I press enter here. Oh, I thought it would. Did not. And now up here we'll enter 25 thirds. And that gives us a larger revenue, a larger return than for putting $10 million into luxury condos and $15 million into low-income housing. Finally, our last corner point here was 10 and 5, which we can already assert at this point that corner point is going to put us in a worse position than this one right here, because of the fact that I'm still putting $10 million into luxury condos, but in this ordered pair, I'm only putting $5 million into low-income housing. And we know that the more we put into each of them, the better off we are in terms of return. So 10 and 5, we're going to expect this to be lower than both of the pairs above. And it is. $1.7 million is our return. So our optimal solution here is to go with 50 thirds and 25 thirds, so approximately $16.67 million and $8.33 million into the two forms of housing. So we see that if they put 16.67, we'll say approximately $16.67 million into luxury condos and about $8.33 million into low-income housing, the optimal return will be what did we find? $2.833 million. Will be about $2.83 million. That's how much they're going to get back in that investment return. We'll go ahead and stop the video here. In the next example, we'll consider one where we have an unbounded feasible region, and the fundamental theorem of linear programming tells us what to do when our region is bounded, but how do we handle an unbounded feasible region? Well, it turns out that in a lot of cases, it's not going to be much different than what we've already done.